Now we're going to talk about a very important theorem in calculus. Okay, section 5.3 is about the fundamental theorem of calculus. Now there are two parts to this theorem. There's a part one and a part two. Okay, we're gonna go through part one, see what it does for us, but it's part two that we really are interested in. Okay, in part two, this gives us an easy way of evaluating a definite integral, where we don't have to find the limit of sums, okay? And we're gonna go through the proof of that when we get there. Show you how the areas are related to the antiderivatives, the things that we were talking about in 4.9, okay? So this is the fundamental theorem of calculus, part one. Okay, first part. Now, it says, if we read it, if f is continuous on a to b, then the function g, defined by g of x, is equal to the integral from a to x of f of t dt, is continuous on a to b and differentiable on a to b, and g prime of x is equal to f of x. So this is what the first part of the fundamental theorem of calculus is saying. It is saying that you could take the integral and turn it into a function. When you turn it into a function, this function happens to have the properties that it's continuous and differentiable on the same interval that f was defined. Okay? Now, when you integrate this, you see there's t's here. Those are dummy variables for right now. When you integrate it, this is going to be a function of t. You're going to take the integral, and then from a to b, it's x right here. So what you're going to do is you're going to end up with a function of x. Okay? Let's see. Let's go ahead and see what we mean by this, that this is a continuous function. We're going to do a problem, but this is much like when we were talking about the derivative as a value as opposed to a function. If you go back to 2.7 and 2.8, in 2.7 we were finding the derivative like this: f of a plus h minus f of a divided by x minus a. Took me a second to remember that. So that's how we were finding there's a limit here. It was the limit as x goes to a. There we go. F prime of a, not c. There we go. So when we find the integral from a to b of f of x dx, this is just going to give me a value. Okay, just a number. The area from a to b. Just like this, when I plugged in a, it just gave me a value. What is the derivative at this value a? And then what we did in 2.8 is we extended this idea to make it a function where that was x, and down here was h went to 0. So we rewrote the derivative as a function of x. Well, that's all we're doing here. I gotta change these to t's, x, and we're saying that that is g of x. That's all we're doing. It's very analogous. We're saying that when you take the integral, you could treat the integral as a function of x. So let's go ahead and do a problem. This is problem number 2. It is on page, let me see, 399 in your book. Let's see, it says, let g of x equal the integral from 0 to x of f of t dt. And they, whose graph, where f is the function whose graph is shown. And then they show us the function, okay? I want to do my best to draw this. This one's going to be probably a little bit difficult to draw. See, that's 1. I go down to -1. That's 1. There's that piece. And 1, 2, 3 goes through here. 4, 5, 6. 4, 5, 6. It's at a maximum of 1, 2, 3. 1, 2, 3. So let's see right there. It goes through 4. And then at 7, it takes a sharp turn down like that. Okay? Now what it wants us to do is evaluate this g function at x equals 1, 2, 3, 4, 5, and 6. And then it says estimate g of 7. So g of, I'm not going to write every single one of these out, but g of 0. Let's talk about that one real quick. That's going to be the easiest one. G of 0 is the integral from 0 to 0 of f of 0, or sorry, not f of 0, f of t dt. If you go back to the previous video and look at the properties of integrals, we know that this is 0. Integral from the same limit to the same upper limit is always equal to 0. So let's go ahead and record that. Let's record it down here. G of 0 is equal to 0. Let's find g of 1. So all I'm going to do is plug in 1 right here. That means this up here, I plug in 1. So now since it's a graph, all we're doing is finding area. In your picture that you have in the book, it's nicely gridded. So we can see that this is a 1 by 1 square. Half of that, this area right here, is equal to 1/2. 1 by 1 square, the area of this square is 1, cut it in half is 1/2. So g of 1 is equal to 1/2. Let's find g of 2. So you can see this is just a similar process going over and over. You plug in 2 here. So this is g of 2. So g of 2 is the integral of this function. So all we're doing is finding the area, the total area, the net area from 0 to 2. Well, this is a positive 1/2. Down here is a negative 1/2. And just look at the triangles. So this is also equal to 0. So let's go ahead now and find g of 3. Well, g of 3 is this next area right there. It's this area, which we know is 0, plus this area. This area is negative. So g of 3 from 0 to 3, that's negative 1/2. Because this area, right in here, the really dark one, that one is also 1/2. So right here is negative 1/2. Right here is negative 1/2. So let's go ahead and find, see, they have us do 4. 4. So the total area, g of 3, starting to run out of room to put these. So g of 4. Now we go over to 4. Right there. And if you look at 4, it also cuts halfway through a box. So this area right here is a positive 1/2. So you can see if I added on positive 1/2 to my previous term, I'm going to get 0 again. And now it asks me to find g of 5. G of 5. Let's see, 4, 5, 6, 7. G of 5 is a trapezoid. If you look here, I'll outline it in a different color. It's a trapezoid. Right there, right there, right there, and right there. The area of a trapezoid is 1/2 the height. The height here is, right here's h, there's B1, there's B2. 1/2 base 1 plus base 2. Well, the height is 1. That is the distance right here. Each height is 1. So if I plug 1 into here, I get 1/2 times 1. The first base, well, this has a height of 1. This has a height of 2. This total has base 1 plus base 2 is 3. So 3 times 1/2 is 3 halves. So the integral from 0 to 5, if I add on from my previous area, 0, if I add on 3 halves, 0 to 5, the integral is equal to 3 halves. So now we have g of 5. And lastly, it asks us to do g of 6. Again, that is another trapezoid. So you need the area formula for a trapezoid. The height right here is 1. All the heights are 1. This is B1. This is B2. So if I were to recompute the area of this last triangle, you get 1/2 times 1. This goes up 2, plus this goes up 3. This right here is a 5. You get 5 halves. So then you add it on to the previous area. So the integral from 0 to 6 is 5 halves plus the previous area, which is 3 halves, or we get a total of 4. G of 6 is equal to 4. So all I'm doing is plugging in 1, 2, 3, 4, 5, and 6 and calculating the areas. Since I have it on a graph, I'm calculating the areas by shapes. Triangle, 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 trapezoid, trapezoid. Found the area of every single one and just kept adding them to the next value. Okay? I started out with g of 0. It was 0. I found g of 1, it was 1/2. Or g of 1 is 1/2, but when computing this area, I add this one plus this area, you get 1/2. You find the next area is negative 1/2. So negative 1/2 plus 1/2 gave you 0. And you just keep that process going and going. Now we also have one more area that we have to find. It's this area right here, this irregular shape. They told us to approximate it, okay? How I'm going to approximate it is I'm just going to make a rectangle that goes like this and like this. The length is 1 and the height is 3. So what I can say is the area of this rectangle is approximately 3. So if I were to go to 7 now, well, from 0 to 6 was 4. From 6 to 7 is 3 more. So the integral from 0 to 7 is approximately 7. Okay? It's approximately 7. We're missing some area here. We're missing some area over there. So again, it said estimate. It doesn't have to be exact. So we no longer need the graph. We need our values.